Hello, my name is Tamir Shukla and this is Lab 6 for Physics 2212 at Georgia Tech. Purpose and aim. Demonstrate electromagnetic induction using Faraday's and Lenz's laws. Observe magnetic damping as a falling magnet induces currents in a conductive tube. Compare experimental times with a computational model. Investigate how a changing magnetic field induces an electromotive force in a conductive loop. Formulas used. We use Maxwell's Faraday's equation, or the line integral of electric field or the voltage equals to negative d phi over dt, where phi b is the magnetic flux, force due to gravity, mg, Ohm's law, V equals to IR, Lenz's law, which is just Faraday's law, inducing sign as well, and we also use magnetic field to a dipole from lab 4. Experiment, Faraday breaking. System is a rare earth magnet. Surrounding its earth is an aluminum foil, and essentially, if you can see the photo, a piece of magnet is dropped, and yeah, and then the average falling time, and the falling time is recorded. So in possible errors could be due inconsistent placement of magnet above tube, lock to video frame rate of phone, or measurement errors. Closed loop simulation. So we determined dipole moment nu from simulation from lab 3, and using that we get nu equals to 2.635. Using this formula, which is the magnetic field due to a dipole at any point r, we have that in the simulation, and this is the rest of the code where we calculate dipole B, then we calculate the flux, and then we have a loop. Yeah, pretty straightforward. So Gaussian simulation, if you want to watch this again, this is a simulation of the magnet falling down and the induced charges at in the tube. Then this is a velocity versus time graph. Simulation time is 0.729 seconds. And the experimental was 0.71, which is very accurate. Some of the sources of error here could be first two experimental attempts, magnet rubbed against the tube. Starting height of magnet probably different between trials, and glow strip start height may be different. Some of the what if questions from this lab is what if the resistivity of the conductor were reduced as close as possible to 0? So how would the dynamics of the falling magnet change? So the resistivity changed from, let's say, 2.65 to so when the resistivity changed from 2.65 to 10 to negative 8, time varies significantly. So as resistivity increases, the time in the tube approaches infinity. So much larger induced current is produced, and this causes much larger opposing force to weight. So essentially, if resistivity is close to possible to 0, then you would have it wouldn't fall. What if the holes or slots were current in the tube? How does it affect the ring currents in your model? So induced currents cannot be formed on non-closed objects. So areas with holes or slots will no longer induce a current, no loop. And when the magnet is adjacent to its the magnet will experience 0 because the magnitude of the force is 0. Acceleration will be stop and go, so depending on what the magnet is closest to, slot was closed, as well the magnet would fall down faster in the cube. So that just really depends on the shape. Yeah, that's all. Thank you.